Good day, everyone, and thank you for making out time to attend this workshop. I welcome you all, and I want you to relax and settle in because what we are doing today is not rushed and it's not theoretical. This workshop is designed to walk you through how industrial automation really works in the field, starting from the process itself, then moving through electrical and mechanical systems, and only then arriving at PLCs, HMIs, and SCADA. I intentionally structured this session this way because in real plants, automation does not start from the software. It starts from process needs, mechanical realities, and electrical constraints. And the control system only comes in to manage what already exists physically. So our goal today is not to teach you everything, that will be unrealistic. Our goal is to help you see the full picture, understand where you currently stand, and clearly see what skills separate site-ready engineers from those who only understand automation on paper. So as we move from slide to slide, you'll notice a smooth story. Each, each section leads naturally to the next, just like it does on site. And by the end, you should feel informed, challenged, and honestly curious to go deeper. So let's begin from the foundation, which is the process itself. Okay, so before PLCs, before HMIs, before SCADA, there is the process. And every plant exists to move, heat, cool, separate, mix, or transform something. All right, so automation does not create the process, it only controls it. And if you don't understand the process, you are essentially trying to control something you cannot explain. That is why strong automation engineers are first grounded in process, electrical, and mechanical fundamentals. So this foundation effective determines how effective your control decisions will be later. So now let's talk about why these skills truly matter on site. Now on site, automation engineers deal with real physical systems, vibrations of pipes, motors overheat, instruments drift, and cables loosen. So most plant problems are not software problems. They are caused by wiring issues, instrument failures, grounding problems, air supply loss, or mechanical wear. Now, when you understand hardware, technicians actually respect you, and operators trust you, and then supervisors rely on you. And this is the understanding because it begins with instrumentation, which is the plant senses. Okay, so moving further, talking about the process instrumentation, which is the plant senses, we use instruments, and instruments are the eyes and ears of the plant. They tell the control system what is happening in the real world. So if an instrument gives wrong information, the PLC will act, but it will act wrongly. So a site-ready engineer can recognize instruments both on drawings and physically in the field. Now this knowledge separates engineers who can solve problems from those who only escalate the problems. So let's briefly look at the main process variables every plant depends on. Before we go further, let me slow this down and explain what we mean by these terms in very simple language. So every industrial process is basically trying to control four things: pressure, level, flow, temperature. All right. So for example, how much pressure is in the system, how much material is present, how fast is it moving, how hot or cold it is. Now these four are what we call the process variables, like I mentioned earlier. So the pressure tells us how much force the fluid or gas is exerting. Level tells us how much material is inside a tank or vessel. Flow tells us how fast material is moving through a pipe. And temperature tells us the thermal conditions of the process. So to measure these variables, we use instruments. All right, so instruments are measurement devices. So we use instruments. Now, pressure can be measured using gauges and transmitters. Level can be measured using radar, differential pressure, or float-based instruments. Then for flow measurements, it depends on the process conditions. So we could use an orifice plate or a magnetic meter, a vortex or Coriolis meter. While temperature is commonly measured using RTDs, that is resistance, um, tem, resistance transmitters and thermocouples. All right. Now at this stage, I don't expect you to know how each one works internally. What I want you to understand is this: if the measurement goes wrong, every control decision that follows will also be wrong. Alright, so once measurements are taken, the plant must act on those measurements. And that action happens through what we call valves. Alright, so moving further, what are valves? We have control valves. Alright, so control valves are simply devices that physically change the process based on a control decision. So if the system needs more flow, a valve opens. If it needs less flow, the valve closes. Now, the valve is what turns a PLC decision into real physical action. So to move these valves, we use actuators. And some actuators use air pressure. So we call those types of actuators that use air pressure pneumatic actuators, while others use electricity, and those are electric actuators. So an important concept here is the fail action. Now, when air or power is lost, should the valve fail open or fail closed or stay in its last position? So this decision is never about convenience. It's always about safety. All right, because many unstable processes that appear to be PLC or tuning problems are actually valve or actuator issues. So to understand how all these instruments and valves are connected, engineers rely on drawings, which takes us to the next slide. Okay, so before you step on site, there is one drawing you must be comfortable with, which is the P&ID. Now, P&ID stands for piping and instrumentation diagram, and it is not a wiring diagram, it's not a wiring diagram, and it's not a layout drawing. It is a functional drawing that explains how the plant is intended to operate. Now, on a P&ID, you will see pipes, equipment, instruments, valves, and signal lines. You will also see instrument tags that tell you what each device does and how it is connected in a control loop. So when a problem occurs on site, engineers do not guess. They go back to the P&ID to understand what should be happening versus what is actually happening. So if you cannot read a P&ID, you are effectively blind on site, no matter how good your PLC skills are. So once equipment is installed according to the drawings, the next step is to confirm that signals are working correctly. And that takes us to the next slide, which is the loop check and basic calibration. So what is a loop check? A loop check is a test that confirms a signal can travel correctly from the field instrument through the wiring into the control system and back out to the final control element. So in simple terms, we are asking when the instrument changes, does the PLC see it correctly, and does the output respond as expected? Now, basic calibration ensures that instruments report accurate values. Zero and span checks are performed so that what the instrument measures matches reality. All right, so going further, most commissioning problems are not logic problems. They are loop problems, which could be swapped wires or wrong ranges or calibration errors. And most modern instruments offer diagnostics, but they still rely on good fundamentals. So if you can remember the checklist I shared with us earlier, some some weeks back, it carried some things that you just actually truthfully tell yourself, okay, I know this, I know this, I know this, I know that, and this will help you like take a proper step in developing your automation and instrumentation career in 2026. So moving further to the next slide, moving to the next slide, okay, we have the HART, HART. Now, HART is a communication protocol used with many field instruments, and HART stands for Highway Addressable Remote Transducer. And like I said, it's a communication protocol, and in simple terms, it allows digital communication to ride on top of the traditional 4 to 20 milliamp analog signal. So I'm sure if you're new to automation and instrumentation, hearing 4 to 20 milliamps may sound, it may sound strange to you, but these are analog signals. So a digital communication, a digital signal is riding on top of an analog signal. That's what HART communication protocol does. All right, so this means that we can read diagnostics, configure instruments, and verify settings without removing the instruments from service. So that's what the HART communication protocol does. However, this is very important, okay, because HART does not replace good installation practices. So if the wiring is poor, or the grounding is bad, or the loop is incorrectly connected, HART will not save you. The fundamentals always come first. So you need to know how to terminate your cables, do your grounding properly, and all of that. Okay, so to understand why we need to look at the electrical side of, or to understand why we need to look at the electrical side of automation. Okay, and this takes us to the electrical hardware skills and reality on site. Many people, electrical engineers, they may not really know or understand how to, express their hardware skills on site. So when automation fails, very often the root cause is electrical. Panels, cables, terminals, and power supplies, they keep automation systems alive. So now, poor wiring causes faults that appear and disappear. It can waste time, and it can also frustrate operators. But automation engineers are frequently expected to troubleshoot electrical issues. Even though that's not like your core strength, but you are expected to be able to troubleshoot electrical issues, even when the electricians are available. So this means you must understand what is inside the panels and how signals and power are distributed. And how can you know this? We have electrical drawings that guide this. All right. So moving further, electrical drawings and wiring diagrams, just like we introduced from the previous slide, they are about the hardware and what you're going to see. So now the question is, how do engineers know how everything is connected? Now that is where the electrical drawings come in, like I said. Now electrical drawings are simply maps. They show us how power flows and how control signals move from one device to another. So when we say power drawings, we are talking about drawings that show how equipment is energized. All right. When we say control drawings, we mean drawings that show how signals are wired between instruments, PLCs, relays, and actuators. So you will often hear the words schematic and layout. A schematic explains logic and electrical relationships, while a layout shows physical placement inside a panel or cabinet. Confusing the tool is one of the fastest ways to make wrong decisions on site. So you need to understand this. Now, once you understand drawings, the next thing you must understand is the actual equipment those drawings represent. So let's talk about the physical equipment we keep mentioning. Now we see a control panel. And what is a control panel? A control panel is an enclosure that houses PLCs, programmable logic controllers, power supplies, terminals, relays, I/O modules, that is input and output modules. It is the brain of the cabinet of the automation system. So this is what a control panel is. Now, MCCs, which means motor control center, is used to start, stop and prevent motors and protect motors, especially large motors. Okay, and a VFD, or a variable frequency drive, is a device that controls motor speed and torque by varying the frequency supplied to the motor. So understanding how power and signals flow through these systems help you troubleshoot intelligently instead of randomly. But knowing equipment is not enough. How it is wired matters even more. Okay? And that takes us to panel wiring and fault tracing. So let me bring this closer to real site experience. Panel wiring is where many automation problems begin. Now, when we talk about wiring, we mean how cables are terminated, labeled, routed, and secured inside panels. Loose terminals, poor labeling, and bad workmanship create faults that appear and disappear. But fault tracing, like I said, simply means following a signal step by step until you find where it is lost. And good fault tracing is systematic. You don't guess, you test, you confirm, and you move logically. So to do this safely, engineers rely on measurement tools. So the next slide, we're going to look at some measurement tools like the multimeters and the process calibrators. So a multimeter is a basic electrical tool used to measure voltage, current, and continuity. It tells you whether power is present and whether connections are intact. Okay, so a process calibrator is used mainly in instrumentation, and it can simulate signals like the 4 to 20 milliamp that I mentioned earlier, so you can test systems without disturbing the actual process. Now, these tools remove assumptions, they help you confirm reality, and always remember, safety comes before speed. All right, so one area where measurement mistakes cause serious problems is grounding. And like I said, I'm going to be taking you through like it's a story. So we are now going to be talking about grounding. Now, grounding and earthing are safety concepts. I'm sure many of us have interchanged, its use. All right. So, but grounding provides a reference point for electrical systems and protects equipment, while earthing protects people by safely directing fault current into the ground. So I want you to understand the difference between grounding and earthing. Now, in instrumentation, grounding also affects signal quality, and poor grounding will introduce noise, false readings, and random trips. So many problems blamed on the PLCs are actually grounding problems. And to understand why faults happen the way they do, we must understand mechanical systems. Remember, I told you we're going to take this, as it's supposed to be. Now, moving further to mechanical and process understanding, I would like to bring back something very real. So before any PLC logic, before any wiring, before any screen design, there is always a physical process happening. Something is moving, something is flowing, something is heating, something is cooling or rotating. Now, mechanical and process understanding simply means knowing what the plant is actually doing. So if you don't understand how a machine behaves physically, automation data will never fully make sense. Sensors will, sensors will make alarms to trip, valves will move, but the reason behind those actions will be unclear if you don't understand how the machine behaves physically. So good automation engineers, they think mechanically first, then electrically, and then logically. So once we understand this, we will now move further. We'll now be moving further to look at some of the most common mechanical equipment that we find in plants. That takes us to the next slide that talks about pumps, compressors, and rotating equipment. So almost every industrial plant relies on rotating equipment, and almost all industrial plants, have pumps, which are used to move liquids. Compressors are used to move or compress gases, and both of them depend on rotation, which has to do with shafts, bearings, and motors working together. So these machines are sensitive, and they don't like running dry or dry running or excessive pressure or overheating. So automation systems are designed to monitor these conditions to protect these equipment. So when a pump trips, it is often the mechanical system asking for help, not the PLC making a mistake. So beyond rotating equipment, plants also rely on stationary process equipment. That takes us to heat exchangers, separators, and valves. Not everything in a plant rotates. Okay, so a heat exchanger transfers heat from one fluid to another. A separator divides mixtures such as oil, gas, and water into separate streams, and valves control flow pressure, and the direction of flow. Now, these pieces of equipment shape how the process behaves. So when they malfunction, the effect is seen across the entire system because pressures will rise, temperatures will drift, and alarms will appear. Now, to understand these reactions properly, we need to see the plant as a continuous flow. Now, process flow is the story of the plant, and it describes how raw materials enters, how these raw materials move through equipment and exits as a finished product. Now, plants do not operate in one steady condition. They have startups, shutdowns, and abnormal situations. So automation logic changes based on these operating modes. Now, when an engineer understands the process flow, they can predict problems even before alarms occur. This now naturally brings us back to safety and protection philosophy. So let me slow down here with a simple picture. Imagine you are on site and suddenly there is a power failure or the instrument air supply drops. At that moment, the control system cannot think or calculate or ask questions. So the plant must already know what to do. That is what valve fail action means. So a valve can be designed to fail open, can be designed to fail closed, or it can be designed to fail in its last position when power or air is lost. This decision is not about production or convenience, it is purely about safety, protecting people, equipment, and the environment. This is why process safety always overrides production targets. Now, what do we understand? Or now that we understand, now that we understand how plants protect themselves, all right, during failure, we can now move ahead to talk about the systems responsible for making everyday control decisions. And that leads us to PLC, HMI, and SCADA. So at this point, everything we've discussed, the process, the mechanical, the electrical, and safety comes together. Now, a control system sits on top of all these layers. A PLC, which means programmable logic controller, is an industrial computer that reads signals from the field and makes control decisions. An HMI or human machine interface is what operators use to see what is happening and interact with the process. SCADA, which stands for Supervisory Control and Data Acquisition, provides higher level monitoring, history, alarms, and supervision across the plant. So these systems do not replace process knowledge, they only depend on it. So to understand why PLC skills are so valuable, we need to understand what industry actually expects. Now that brings the question, why does automation and PLC skills matter? So many people learn PLC programming, but the industry looks for something deeper. PLCs control real equipment and safety critical operations, yes. A small mistake can shut down production or damage assets. That is why industry rewards engineers who can troubleshoot calmly under pressure, not those who only hold certificates. Alright, so poor automation skills result in downtime, unsafe conditions, and loss of trust. And all of this is guided by a concept called control philosophy. So this explains why automation and PLC skills matter. Moving further to understanding industrial control philosophy. Now, the control philosophy describes how a plant is intended to behave. It defines what is controlled automatically, what is only monitored, and what conditions will trigger protection or shutdown. So the control philosophy also defines the difference between control systems and the safety systems. A key principle is this: control logic must always fail safely. Now, applying this philosophy correctly, we must understand how the PLCs actually work. Alright, so that takes us to the PLC basics. So a PLC is not a laptop or a desktop computer. A PLC is designed to run continuously, sometimes for years, in hot, dusty, and noisy environments. Now, the PLC works in a repeating cycle called the scan cycle, and it reads inputs, executes logic, and updates outputs over and over again. So it works with digital signals, which are on and off, zeros and ones, and analog signals, which also change gradually, because the PLC does exactly what it is programmed to do. So clarity in logic is very critical. This is why the industry still prefers a particular programming style, which I'm introducing to you in the next slide, which is the ladder logic. So like it said, ladder logic is still key. Now, ladder logic is a programming language that visually resembles electrical relay circuits. It is widely used because it is easy to read, easy to troubleshoot, and easy for maintenance teams to understand. So clear ladder logic allows engineers to quickly find faults. Messy logic slows everyone down and causes production losses. So safety and protection logic are built on this clarity. And this brings us into what we call interlocks and trips. Now let's define these terms clearly. What is an interlock? An interlock prevents an action unless certain conditions are safe. A permissive is a condition that must be true before equipment is allowed to start. A trip forces equipment to shut down when unsafe conditions occur. Now, good automation engineers always ask one question while designing logic: what can go wrong? That's always the question a good automation engineer will always ask. And that question leads directly to a fail-safe design. Now, what do you understand by fail-safe logic and design? So let me explain it this way as it usually shows up on site. So let's imagine you arrive a plant in the middle of the night and production has stopped and everyone is tense and someone says, the system just tripped. The first question a good engineer will ask is not who caused it, but did the system behave safely? That question is the heart of the fail-safe logic. So fail-safe design means deciding in advance how the system should behave when something goes wrong. That is when there is a loss of power or a broken cable or failed sensor or software error. The rule is simple. When in doubt, the system must move to a safe condition. And in industries like the oil and gas, fail-safe design protects lives, equipment, and the environment. So it is not optional. To design fail-safe systems properly, engineers must trust the signals coming from the field. Now that leads us to the analog signals, which are the 4 to 20 milliamps signal. Now let's pause here and define what we mean by signals. So an analog signal represents a value that changes continuously. Alright, so things like pressure, temperature, level, or flow. They are not digital signals like zeros and ones. They could be vary continuously. You could have 1.1 psi and then it increases to 1.5. Alright, so the most common analog signal used in the industry is the 4 to 20 milliamps. Okay, so engineers use this range because it is reliable and allows fault detection. So if a signal drops below 4 milliamps, the system knows something is wrong. And this signal is sent from instruments like the pressure transmitters to the PLC. Now, if analog signals are misunderstood, automation decisions become unreliable. So to understand these signals correctly, software must be well structured. Yeah. And that takes us to PLC software platforms. So now that signals are coming into the PLC, the next question is, where does the logic live? So different manufacturers provide different PLC software platforms. For example, Allen Bradley Systems use RS Logix or Studio 5000, while Siemens use the TIA Portal. Okay. Now these platforms are tools used to write, organize, and test control logic. Now while the screens may look different, the principles are the same: clarity, structure, and maintainability. So before any logic controls real equipment, it has to be tested. Now that takes us to the simulation and testing. Now simulation is like rehearsing before a live performance. So it allows engineers to test PLC logic without connecting to real motors or valves or the process itself. Now during simulation, you can confirm that interlocks, permissives, and trips behave as expected. So good engineers test first, then they trust, their logic. So once the logic works correctly, operators must interact with it. And that takes us to why HMI and SCADA matter. Now let me paint a very familiar picture. Imagine you walk into a control room for the first time and you see multiple screens. Numbers are changing, alarms are blinking. At that moment, the entire plant is being represented on those screens. That is where HMI and SCADA come in. So an HMI means human-machine interface, and is simply the window through which an operator sees and controls the process. A SCADA system, which stands for supervisory control and data acquisition, it sits above the control system and provides plant-wide monitoring. It monitors the alarms, the trends, and also, the historical records. So if anything happens, you can trace through the SCADA. So these systems do not control the process directly. They only support human decision making. So if the information presented is unclear, even a well-designed PLC system can be operated wrongly. So the next logical question becomes, how do we design HMIs that humans can actually use effectively? That leads us to operator-friendly HMI designs. Now this slide is about designing for people, not machines. So operator-friendly HMI design focuses on clarity, simplicity, and consistency. Now a good HMI design means operators can understand what is happening within seconds, even under pressure, and it avoids unnecessary colors, animations, and clutter. Good HMI design has clear labels and the symbols are consistent. So the symbol for a valve is consistent in all the screens. Navigation is simple. But when the HMI design is poor, operators hesitate. And when it is good, they respond confidently. Now, a major part of good HMI design is how alarms are handled. So I'm taking us step by step on these things so that we will be able to use our checklist to ask ourselves the truthful question if we have all of these things covered to excel in our career in 2026, or if we need to buckle up to understand these things and position ourselves for for better opportunities in this year 2026. So let's clearly define these two terms. An alarm is not just any warning, it is a condition that requires immediate operator action. And a trend is a graphical display that shows how a process value like pressure or temperature changes over time. So trends help operators see problems developing before alarms even occur. And if alarms are too many or poorly prioritized, operators become overwhelmed. And this is why alarm management follows specific standards. Now that leads us to the ISA 101. Alright, now the ISA 101 is an international standard that provides guidelines for effective HMI design. It focuses on human factors, how people perceive information, make decisions, and respond under stress. So alarm management standards help engineers decide which alarms truly matter and which do not. Standards bring consistency across systems. So to apply these standards properly, systems must be properly connected. Now we move into what we call the PLC and HMI integration. So the PLC, which is a computer on its own, must interact with the HMI. So let's imagine something very practical. An operator is staring at an HMI screen and sees a pump shown as running. That is, the pump is indicating that it is running, but on the field, the pump is actually stopped, it's not running. Immediately, there is going to be confusion and there will be delay and a possible risk, a hazard. So this situation usually points to a problem with the PLC and HMI integration. So remember I described the PLC as meaning the programmable logic controller, and it contains the actual control logic that controls the process. While the HMI, the human machine interface, does not create information on its own. It only displays what it receives from the PLC. So what does integration mean? Integration means correctly linking PLC variables, which are called tags, to the objects you see on the HMI screens. Now, when tags are wrong, outdated, or poorly mapped, operators are misled. So PLC HMI integration is about trust, and operators must trust what they see. Okay. Now, when that trust is broken, the next skill an engineer must rely on is troubleshooting. Now, troubleshooting is not about panic. It is about thinking clearly under pressure. So when something is not working on an HMI or SCADA system, experienced engineers follow a simple order. First, they check communication, then they check PLC status, then they check field signals. Okay? Now, SCADA, which stands for Supervisory Control and Data Acquisition, as I mentioned earlier, often sits on top of multiple PLCs and networks. So because of this, many problems appear on SCADA screens, even though the root cause is somewhere else. Now, good troubleshooting means asking the right questions instead of making assumptions. And once issues are resolved, engineers often reflect on how prepared they really are. Now that takes us to a checklist reflection. So this slide is a pause, and that pause is intentional. Alright, it is a moment to honestly assess your current level. Can you explain a process clearly from start to finish? Can you understand how instruments, electrical systems, PLCs, and HMIs work together? Can you calmly troubleshoot when something goes wrong? Now, these questions are not meant to discourage you. They are meant to show you the gap between awareness and true competence. And that brings us to my final message. So, this workshop is not about making you an expert overnight. It is about helping you see the full picture, how process, mechanical, electrical, and automation systems connect in real plants. Now, it gives you language, structure, and confidence to continue learning correctly. So, real competence is built through guided practice, real examples, and repetition. And that is what the full training is designed to provide. All right. So, learning automation is a journey, not a single event. And the next step is a structured training that takes you from fundamentals into hands-on PLC programming, HMI development, and real troubleshooting scenarios. All right. And this part is designed to help you move from watching systems work to confidently working on systems, passing your interviews, getting that dream job. So finally, let me leave you with one thought. All right. Now, every control system you see in industry today was designed, was programmed, was tested, and commissioned by engineers who once stood exactly where you are today. Now, the difference between curiosity and capability is guided learning and deliberate practice. So, if today's session helped you see things more clearly, then it has done its job. All right. Now, I really want to thank you for your attention, and I look forward to helping you take the next step. So, if this is you and you are willing to take the next step, which is enrolling for the training, you know, then click on the link in the description to take the next step. And once again, thank you so much for attending this workshop and have a great day.